Okay. Well, thanks everyone for joining us. Jason, just to confirm, I'm visible and my slides are visible.
Yes, sir.
Okay, great. Thanks for joining us this morning. I'm Steve Reinhardt. I'm VP of Product Development at Quantum Computing, Inc. Today we'll have my colleague Uchenna Chukwu is going to be walking us through a demo of our new Mukai constraint optimization interface, and show you how to solve problems that way. Thank you for joining us. If you have any questions, that was our colleague Jason Bay, who is sitting there in the background and is monitoring the chat window, and will feed questions in as we're going through this so that we can get those answered. We'll probably mostly do clarifications during the talks, and then we'll answer any questions we have at the end. So what we want to talk about is accelerating constraint optimization with quantum processors. So I'm going to talk a little bit about what we're doing as a company with our technical strategy, and then Uchenna will dive into some actual problem solving. So roughly what we're going to cover here is what our mission and approach are at QCI, our technical strategy, solving problems, and a little bit about applications at the end. So, you know, we quantum computing enthusiasts, we often talk and get excited about scaling to the amazing heights that quantum computing will enable. And I've drawn that as this arrow pointing at the top of a peak. That's going to be the amazing thing that'll be there. And you know, this is a reasonable thing. We're all humans. We're not computers. Excitement, passion are a key part of getting a hard problem like quantum computing solved. But it can be easy to overlook that kind of idyllic mountaintop of quantum advantage is eventual. And the first uses of these small, noisy, not robust quantum computers will struggle mightily to get a modest amount of benefit even after lots of work. So sticking with the mountain theme, I kind of think of this as we're here on the near side of this chasm, and our first steps are actually going to go down. They're going to get us below where we want to be. So what the first step is just to make it over there to the other side of this chasm. And I think of that as the place where we know how to use quantum and classical hybrids beneficially. And then at that point, as the quantum computers get lots better, and we have actual quantum advantage, then that's where we get to the mountaintop. So we're kind of focused on this current reality of how do we get over this chasm, but we have our eyes on that mountain at the end too. And so I guess, you know, again, to continue with the mountain metaphor, we kind of think of this at QCI as we need to build bridges from the things we already know how to do well, which are classically, and then how do we incorporate quantum computers into that and have an overall benefit. So this is the third picture here is kind of our preferred path is we're already, you know, computing has done a lot in the last 50, 60, 70 years. We want to take advantage of all of that and be ready to take that next wave of quantum computing to even higher levels. So obviously this is kind of hand wavy, you know, intuitive, but that's what we're trying to do. Our mission at quantum computing is to deliver superior performance now from quantum ready applications and tools. So superior performance now, that's pretty clear. Quantum ready is a term you may not have run into. So define that at the bottom here. What we mean by that is developed using methods that map directly to quantum computers. So there are no, once you write an application in a quantum ready method, there's no application level changes you need to make to execute on a quantum processor. So some of the things this allows us to do, you know, we want to appeal purely classically first because that's what the fastest thing is today. You know, July 14th, 2020, the fastest thing is a classical computer. And essentially every situation that I'm aware of. So we want to get near-term adoption of quantum-ready methods. We have to have better classical performance. Another thing this does is accelerates the routine use of quantum computers when they deliver advantage, because we deal with all the other hybrid stuff now before we have quantum advantage. The other thing is it'll broaden the range of applications able to take advantage of quantum computers, because the software infrastructure and the hybrid nature will be more advanced than it would be if we don't pay attention to it before we have quantum advantage. So that's our mission at QCI. And our Mukai middleware is available in the cloud today, delivering superior performance. So if you want to get started today, that would be great. We'll get you spun up. A lot of times people say, well, why would I have a big problem? What kind of problems do you solve? So this is just a simple example of what we do and in what context it might be valuable. So you'll hear us say constrained optimization a lot. An example of that is logistics. A specific example is you want to deliver packages to locations by vehicles, and you want to account for time and the capacity of the vehicles. So in one particular formulation, you can see the reference at the bottom of the page. Dimensions of the problem are the number of locations you want to deliver to, the number of vehicles you have, the number of time intervals you have, and the capacity of each vehicle. And you might not think that this would get to be a big problem, but here, if we think about the number of variables in this, if we had 500 packages and 20 vehicles, so say that's not quite 30 packages per vehicle, and we have 32 time units we're scheduling into, that's 9.6 million variables. That's a pretty big problem. It's not the biggest ever by any stretch, but that's a pretty big problem. So these problems can get big, and they're pretty quickly. The example of constraints you might have in this particular package delivery is, any vehicle cannot arrive at 2 locations simultaneously. Any vehicle can only arrive at a location once, and only one vehicle will arrive at a location. So those are all constraints that you put on, if you're a subject matter expert, those are constraints you put on the problem. The objective, the simplest one, is to minimize time. You might also want to be minimizing fuel consumption, or some combination of those, or you might also have safety considerations that are taken in there. So there are a lot of ways to define your objective. Are these valuable problems? Well, there was one study from 7 years ago that showed that in the US airline industry that reducing flight delays by 10% would save over $17 billion a year. So to us, that's a yes. There is high value in these kinds of problems. So if you think about the next time there's a snowstorm in Denver or a hurricane in Houston that disrupts airline traffic, and they want to get it online quickly, it takes longer than people would like today, because they can't solve these problems highly effectively. So that's in a nutshell, that's the problem the type of problem we're trying to solve here with our constrained optimization approach. Our technical strategy, so let's go through that quickly. So the big deal with quantum computing is better performance. So when are we going to get that? Well, possibly it could come with the next generation D-Wave processor, sometimes called Pegasus, in 2022 plus or minus. If not then, we could get a performance impact from non-error corrected gate model processors, maybe 2024. These have pretty wide error bars on them. And if error corrected gate models don't help us, then we're out to, or non-error corrected, excuse me, then we're waiting for error corrected gate models, which are maybe another 10 years beyond that. So 2032 with an even wider error bar. So one of our first challenges at QCI is, given this uncertainty in when quantum advantage arrives, we need to insulate application developers and users from that uncertainty. So the next thing we need to do, the kind of second pillar of our strategy, is our middleware must hide enough detail and it must deliver performance. So if you think of this iceberg metaphor that I've stolen from Jack Worrelton from Los Alamos, everything below the waterline is stuff that if you're an application developer, you don't have to think about. You can just focus on the things above the waterline. And in the classical world, there's a rich set of things that you can work with there. If we look at the quantum world, it's much more constrained. A huge amount of the effort so far has gone below the waterline. And so if you just want to deliver an application or you just want to use an application, it's pretty hard going. So we have a combination of things that we're doing. The focus here, the constrained optimization solver, that's what Uchenna is going to talk about in a few minutes. And NetworkX is another high-level API we won't talk about today. And QCD, the quantum community detection application, is something I'll come back to in a few minutes. I don't want to leave the impression that we're the only people dealing with issues above the waterline. TensorFlow Q is a variant of the Google-originated TensorFlow machine learning framework, and there is a quantum angle to that. So other people are trying to do this above the waterline as well. But we view it as we have to insulate application developers from machine-specific details. Next leg of our strategy is deliver superior performance today. So this is a pretty busy slide here. And this is looking at quality of results. So when you try to optimize something, how typically people optimize to the smallest value, and how small is it? And do we do a better job of that than other solvers? So here's an example. So this MQLib is a library of benchmarks out of MIT for constrained optimization. And this left plot is the Mukai results in the blue, showing where Mukai gets better answers, more optimal answers than the best MQLib heuristic. There are 3 in the middle here where we tie, and there are 15 where MQLib heuristics do better. So typically, Mukai gets better answers, not always. On the right-hand side of the slide here, we took those, the 1200 second time limit, and we just said, well, how many of them get answers that are 4 times faster? And it's 21 of the 45 problems ran at least 4 times faster than the best MQLib heuristic. So you can see the reference at the bottom there for that. I'll also put that up at the end. But this is our evidence that we are delivering superior performance today. And then the last leg of our technical strategy is, for now, we're focusing on constrained optimization. Best delivery route, like the logistics example, best schedule for aircraft engine repairs, for example. The best folding of a protein, or best design for a protein. So that's our technical strategy. In a nutshell, all this is available as a working software via in the cloud via quantumcomputinginc.com. So now we want to turn our attention from talking to doing, where my colleague Uchenna Chukwu will walk us through using Mukai's constrained optimization API to solve the traveling salesperson problem, a well-known constrained optimization problem. Uchenna has a bachelor's in physics from University of Maryland College Park and a master's in computer science from Johns Hopkins. He joined us after being one of 2 principals in a quantum machine learning startup, and is focused on performance and constrained optimization among a variety of contributions he's made here at QCI. So with that, Uchenna, take it away. I'll stop sharing and you can share.
Thanks a lot, Steve. Let's start to share my screen. Okay, so today I'll be showing the use of the Mukai software constraint optimization function on a very well-known problem known as the traveling salesperson problem. Traveling salesperson problem, the problem definition of it is given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city? We have the Wikipedia page reference here for further elaboration of this given problem instance. And it's given domains of applications are used in areas of such as vehicle routing, logistics, and planning. And the traveling salesperson problem itself is a very well-known computationally difficult problem to solve. So within the optimization community, we use optimization methods to find approximate solutions for the traveling salesperson problem. And that's where we can use Mukai's constraint optimization solver to help find these approximate solutions. The constraint optimization package available through Mukai is QuoIR. So from Mukai, you import the QuoIR client package. And then here we just have a util function that we use to help build the graph and what we call the objective and constraint portion of the problem instance. And we also use this utils to draw the solution route to a map. So the very first thing we're gonna do is to load the data into a data frame of 16 cities. So define the variable for 16 cities. We have a file of data for the 16 cities that will construct the data frame. So what we have printed to the screen here is just the top 5 instances of the table or / data frame. It's the column of city, state, and coordinate. Within the coordinates, you have your latitude and your longitude. Each row is a city instance with its given coordinates. So you have Albuquerque, New Mexico with its given coordinate. And then you also have Boston, Massachusetts with its given coordinate, and so on. Next, we'll map these cities. We'll draw these cities onto a map. And as we are looking, the question that we're asking is, what is the best route between the cities? So we have these data points for each of the cities, such as Los Angeles, Missoula, Albuquerque, Omaha, Kansas City, Evanston, Indianapolis, Detroit, Frankfurt, Nashville, Huntsville, Gulfport, Pensacola, Charlotte, Jersey City, and Boston. Then this portion, we get to constructing the graph instance. The graph instance is just the distance, it's just vertices and edges, where the vertices represent cities and the edges represent the distance between each city. Here, as you can see, we have number of cities, number of edges, and within the graph object G, we printed a subset of the edges in it. Here we have an edge between city 0 and city 1 with a weighted distance of 2,230 miles, and then city 0 and city 2 with a weighted distance of 1,631 miles. Next, with that graph instance, we then construct the objective portion and the constraint portion of the constraint optimization problem. The objective portion is a matrix that just represents the distances between the cities. So we have a distance matrix that is extrapolated into the objective portion. The constraint is defined within the given definition of the problem as each city is visited exactly once in a given solution, also known as within a given order. So going within a route, going from one city to the next. Each city is visited once and exactly once. So then we construct the objective and constraint portion here. We have the reference here for explaining the objective and constraint portion of how the matrix is defined and formulated. So for more further information about that, this is the reference here. We'll put that in the Slack. Let me put that in the chat. I'll put that in the chat later. And so the size of the matrix for the objective portion is 256 by 256, given within the given definition of how we formulated the problem. And the constraint matrix is a 32 by 257, given by the definition of how we constructed the problem. Now, the key part of the QuoIR, Mukai QuoIR, is you want the function of the sample Lagrange optimization. So here, QuoIR.sample Lagrange optimization is the constrained optimization backend that we are calling to solve this problem. And the required input is the objective part and the constraint part. This divided by the constraint.mean is just us normalizing the constraint part. And the depth part, the max depth, is the number of iterations through optimizing on this problem instance to get your solution. The key part about the sample Lagrange optimization is that it is a linear combination of the objective and the constraint, but it's also tuning a specific parameter to describe the importance of the balancing between the objective and the constraints. And the key part about that balance of importance is to help separate the good solutions, also known as feasible solutions, from bad solutions, also known as infeasible solutions. So that parameter tuning is to help with that key balance to separate feasible solutions from infeasible solutions. But a user is not bounded by just Lagrange optimization tuning for them. A subject matter expert can also specify that parameter him or herself. And we have that function available as QuoIR.sample constraint problem. You also pass in the objective part and the constraint part, but that key parameter tuning is alpha. That is the parameter that is used to help balance the importance between the objective and the constraint to help separate good solutions from bad solutions. So we first defined it up here, and then we run it. It first uploads into the cloud to the backend of Mukai, and then we solve it. And then what we get back is a client response, which contains samples object, array of energies, and array of count. These samples are just an array of solutions. And the solutions are just the bit set for each solution. And those bit sets are to be mapped back into the user domain for them to derive the solution of their problem. The energies are the energies associated with each of these samples. Essentially, energies are just the linear combination of the objective and constraint multiplied by each sample solution. So this first energy is what we would have gotten for the first sample here. And then the second is for the second sample. And these energies, these are just mostly important for the backend solver, because the primary objective of the backend solver is to minimize energy as much as possible. And that has a correlation with the minimization of the objective matrix that is passed in to the sample Lagrange optimization. And count is the frequency of seeing each of these samples, each of these solutions. And this here is just, it's a more so for the subject matter expert, but the samples here is, you have the columns to define the cities. So it's indexed by the cities, and the rows are indexed by time or placement in a route. And each column has only 1 1 in it, and each row has only 1 1 in it. Every other entry are zeros. And what it's saying that, for example, city 0 is the, I think this is the 7th row or the 8th row. So that is the 8th city in a route for a given solution. The city 1 is the 14th city in a route. And if you move all the way over to column 14, that city 14 is the first city in a route. And that's just the encoding technique of the solution for this given problem instance. Now we're gonna map this, we're gonna draw this solution to the map. So as you can see here, we have achieved a route between all 16 cities with a mileage equal to 8,400 miles. The key interesting thing about the return set of solutions here is diversity. And what do we mean by that? Diversity is the fact that if you look at the array of energies within the client response, you'll see that a number of these are equivalent to each other. So the first solution, the first energy is a single one that does not have one equivalent to it. The second one is an energy value that does not have one equal to it. But the third and fourth one are equivalent, and those are solutions that achieve the same distance but are a different route. This is a sampling technique, so different times you run it, you'll see that sometimes the very first 4 energies are equivalent, and those first 4 are the minimal energy achieved. For example, if we run this again, we may see something different. So as you see in this one, the very first 2 energies are equivalent, whereas the very next 2 energies are equivalent. And to give you a better picture of that, first off, let me draw those 5 energies. I'm gonna draw the top 5 on the map, and you'll see what I'm saying. So the first one, the first return solution is a route between all 16 cities with 8,400 miles achieved, and that energy, that's associated with the minimal energy. And remember, the second solution had an equivalent minimal energy, And we see that this is a different route taken, and it's also 8,400 miles. Now, the third solution was a different energy level. So it was the second energy level, and that gives us the second lowest mileage, which is 8,412 miles. And this is the given route for that. And the fourth solution was also equivalent to the third one, and that gives us a route with 8,412 miles through all 16 cities. The fifth one was different. So that was the third energy level, and that one gives us a mileage of 8,424 miles through each of the 16 cities for this given route. So that's the key takeaway of using the Mukai sample Lagrange optimization, or the Mukai sample constraint problem if you already know the tuning of the parameter for separating good solutions from bad solutions. And with that, I hand it back to you, Steve.
Excellent. Thanks, Uchenna.
Yeah.
Let me get to full screen mode here. So, so that was a lot. You know, that's a pretty dense content, and something I think is worth maybe reiterating is that there are these three dimensions of performance that are important. The first one is how good, how optimal is the answer. The second is how long does it take to get that answer, and the third is what we call diversity of solutions, or how many answers do I get with similar levels of optimality that are distinct from each other. And that last one is, I mean, everybody understands, well, getting a more optimal answer is better, getting it faster is better. Why is getting a set of them better? Well, when we hear from customers, there are situations like I mentioned in the logistics context. Well, you may have floods or a tornado or something that's, you know, a weather event that disrupts a route that's being taken. And if you have a variety of solutions, it allows you to add in other types of data like weather data and say which are the ones that are still going to be effective, you know, most robust to some of those issues that might come up. So we've heard from several customers that this what we call a sampling ability, which may be a weird word for some of us. You know, in the classical HPC world, we always think about solving a problem. You give a specific answer that is the right answer, and you kind of get upset if you don't get the right answer. Well, in this world, since we're getting approximate answers, we don't, in general, for large problems, we don't expect that we're getting the right answer. And so that's why we talk about sampling, and even the names of the functions are sample. So it gives you, it just kind of reinforces that notion that you're getting results from a probability distribution. And we think they're good results usually, but they're certainly not guaranteed to be optimal. Something I'm realizing I neglected to mention earlier is Uchenna talked about the QuoIR API library. And so we started out and we wanted to build an API for constrained optimization, and really it's a what we think of as an intermediate representation. So COIR was what we came up with. And then, of course, we're a quantum company, so everything has to have a Q in it. And that got corrupted to QuoIR with a QUOIR. So that's where that came from. So moving on to applications. I mentioned community detection earlier, and we are building an application based on community detection. So community detection itself is a broadly useful technique across many domains. It's believed to match quantum computing processors very well. So we have that kernel available. We're actually deploying it for this use case down here in the lower left. When you're in a drug trial, you have a set of patients that are in it, and it's very high value to be able to find a subset of those patients who are getting benefit from the drug. And so that's what community detection allows you to do. It's a little bit like clustering or a little bit like partitioning, but it doesn't care whether the groups, the communities that are identified are the same size or anything like that. So it's a more powerful technique. We also see that being relevant for epidemiological models, which is everybody's front of mind these days. In the government space, we hear repeatedly that it's valuable for detecting criminal activity, cybersecurity issues, fraud, bot detection, et cetera. So that's the next application we're working on. We have a couple other things that are not yet to that point of active development. Logistics, we come back to repeatedly. Protein design, finding the optimal angle of bonds is often valuable. We appear to be able to do that very well. And then in the scheduling world, job shop scheduling, aircraft repair depots, aircraft crew assignments. And again, to reiterate what I said at the beginning, these are very high value problems. The number of reducing US airline delays by 10% would be worth 17.6 billion. Just in the US, that's just reducing it by 10%. So these are high value applications. We started a free trial of the Mukai software last week based on the recent Mukai 2.0 release, which has this QuoIR interface in it. So simpler, higher level constrained optimization API, which we think it will be a fairly straightforward thing for many subject matter experts to use. There are a bunch of performance improvements in that release as well, and the community detection function. So if you have, if you want to participate in that, send us an email and we'll get you signed up. So to end, our software for constraint optimization is quantum ready and delivers superior performance today, running classically. So you can check us out at quantumcomputinginc.com or info or trial at quantumcomputinginc.com. And with that, we'll take any questions. And I'll leave this up here so you can see some of these pointers to various things. So Jason, do we have any unanswered questions from the Q&A or the chat?
Well, I think Jesse's done a pretty good job fielding a lot of these questions, sort of maybe privately, but if any of the attendees have any questions that they'd like answered, feel free to sort of message us in chat and we can just answer it right here.
Right.
There are a few unanswered ones I haven't gotten to, so maybe it's easiest to answer those if anyone wants.
There it is. Sorry, I was yeah. I'll go to the open now. Do you have data? Okay, so here's one from Michael Ahrens. Do you have data on the time savings of coding the traveling salesperson problem in Mukai versus low-level quantum programming? That is the main value of Mukai. Yes. Also, what is your revenue model for this, or is Mukai open for all? So. So time savings. So we're aware of various people having coded this up. I'm not aware of specific information about how long it took. I know with the Mukai approach, it's I don't know, maybe half an hour to confirm and convince oneself that you have it right. depending on how close to the hardware you get, just doing it at a high level with a QUBO is, which is not a concept we talked about very much, but is the lower level representation that is necessary, for instance, for the D-Wave processor. Just represented as a QUBO is a few days, I guess, in my experience, and that's assuming you do it in a machine independent way. If you go down to actually doing it in a machine dependent way, where you're looking at qubits and couplers and in the physical hardware graph, that is, I would say, probably order of a month of work. So yeah, it's depending on what the alternative programming approach is, it can be, I guess, maybe 1 to 2 orders of magnitude faster, higher productivity for the application developer. So yes, I guess we see that as the main value of Mukai. Some of the things that Uchenna illustrated, like the Lagrange sampler, those are also things that are doable by experts, but by experts. And if you're an expert in one area, you maybe don't want to have to worry about being an expert in some of these other areas. So yes, the main value of Mukai is kind of consolidating that expertise in working software that you can just use. Our revenue model is, this is a cloud-based service. So typically you'd get a subscription and you'd use this as much as you need to. We work with customers to figure out best representations. We have quite a bit of experience mapping problems to these forms. And so, we have some just expertise about programming quantum computers this way. So we also do some consulting in that range, but the main thing is we want to get applications running that use this approach. So today it runs purely classically. When quantum advantage is here, it will take advantage of that. So that answers that. I hope that answers that question, Michael. If not, please speak up. So looking at a question from Greg, have you at QCI tried scaling your compute horizontally, distributed quantum computing, i.e. each single system holds n number of bits? If yes, which distributed framework do you use for this scale out? So unless I'm misunderstanding and Uchenna or Jesse would want to answer differently, my answer would be no. We haven't really looked at scaling the quantum computing horizontally. We have certainly talked, so we've talked about how we can replicate our samplers to give even better performance. And so those would be scale out horizontal distribution. But the number of, so maybe I should give a slightly different answer. So we have thought about horizontal distribution, yes. Today, we've only really looked at that for classical resources because classical resources are abundant and fairly inexpensive, whereas quantum resources are fairly non-abundant and fairly expensive. So we haven't looked at that. But if that were to come to reality, then yes, we certainly could take advantage of multiple QPUs simultaneously. If yes, which distributed framework do you use for this scale out? So far, we're using Kubernetes, and that's probably as much as we want to say publicly. Do you use any quantum error correction algorithms currently? I believe not, but again, if Uchenna or Jesse, if either of you, if I'm missing something there, please speak up.
No, not much. We've talked about, probably starting with out of the box. Can't remember what it's called, but yeah.
There's like gradient descent kinds of things that I know we're commonly done on the D-Wave processors.
Yeah, yes, and also, there's other error corrections that would come in the actual library itself. Depending on sort of what is the desired interface method to the actual quantum computer itself. So
right.
Everyone kind of comes with their own error correction layer. So I guess that's a little tough to answer, depending on the framework, the hardware framework you want to use.
Yep. So to answer another question, will the recording be made available online? Yes. It'll be on the website, on the QCI website. Jason, I'm not remembering.
Yeah, so we're setting up sort of a blog and media page to sort of host these, but the recording is going to be made available sometime tonight. We're going to host it on YouTube. Probably just search up QCI webinar and you should be able to find it. But yeah, it will be made available.
So I'm seeing Michael Aaron's question. If I understand correctly, the TSP was run on classical computers, and in the future using a D-Wave computer using Mukai, we will be able to run it on a QPU. Or is this a hybrid model currently? I assume with the cloud cost, you will embed the cost of renting the D-Wave QPU as well when it is ready. So, so there are a couple answers to that. So the thing we literally, the thing that Uchenna did with his fingertips, 15, 20, whatever minutes ago it was, that was run purely classically correct. We have in the past run pieces of our software stack on D-Wave processor, and we are in the midst of getting it to run on gate model processors. Currently, we don't have that exposed to customers, but that we expect to come over the second half of this year. So today it's not a hybrid model, but we would expect it to become a hybrid model over the course of this year. And yes, you can expect that when we are using a quantum processor, that the cost of that will be incorporated in the cost of Mukai. And I should say, I'm an engineering person. I'm not a marketing and sales person, and so everything I say might be overridden by marketing and sales people. But that's my expectation. Okay, Jason, are any other questions or anything that I'm not seeing? That anything else before we wrap up?
Not that I'm seeing, but John Dawson, who also works at QCI, did mention that we will probably add the ability for customers to add their own QPU. So
yes, excellent point. All right. Well, thank you very much for your time.
Well, actually, before they go, let me just link them the page for the Mukai Trail Access if anybody's interested in sort of getting hands-on. So should be a lot easier to access.
Okay. And my experience with Zoom is you have to make sure you grab that pretty quickly, because once we end the session, I think it disappears. So if you're interested in that, strike while the iron is hot. Okay, Well, thank you, everybody. If you have any questions or anything, please feel free to follow up with us, and we appreciate your time and look forward to having you as a customer before long. Cheers. Bye-bye.